So the concepts in this chapter are going to be very similar to the concepts that we learned in Chapter 9. The primary difference is that now we're going to be comparing two samples. Now, why would we want to do this? Let's say we want to compare two groups. All right, I want to know what is the black-white wage gap. I want to know what is the gender wage gap. I want to know whether or not a drug is good or bad. I want to know whether or not one city has more pollution than another. In all those cases, I never really know what the population parameters are, but I can go out and I can sample from those two groups, right? Now, those two groups are constructed from different people. So I can't just simply take their difference from two random folks and say, okay, I've called out a new person and make a one-sample test. I have to treat those as two independent samples and then make a joint test together. That's what this chapter is going to talk about. So how to use hypothesis testing for comparing differences between the means of two independent populations, the means of two related populations, the proportions for two independent populations, and then the last part, which is going to be new, the variance of two independent populations. Now, we haven't talked about testing variances yet. We're going to start doing that at the end of this chapter. So two-sample tests. If we have population means, we can look at independent samples and related samples. A related sample is when you actually have the same group of people. Just in one case, they are given, say, a control, and in the other case, they're given a treatment. All right, so, for example, let's say we want to look at the effects of job training on folks. All right, we can go out and get a group of people and see what their characteristics look like right now. Ask them how long has it been since they've had a job. What do they get paid at that job, etc. Right? Then we can give them job training, the same group of people. Wait another 6 months and go back and ask them how long you've been searching for a job. If you have a job, how quickly did you find a job? What wages do you have? Since we have the same person, we can take their differences before and after. Those cases are going to be the easy cases, the related samples, because in those cases we can actually bring it right back to a one-sample exam. We can actually take the difference between each individual and make it into a one-sample mean and just ask, is that different from zero? So that's the easy one. The hard one is when I get a group of people who haven't been in Job Corps and another group of people who have been in Job Corps. Those are two different populations, right? Those are not the same folks. How do I treat those two folks when I want to do that same question? So the goal here is to test a hypothesis or form a confidence interval for the difference between two population means. If mu1 equals the mean of population 1 and mu2 equals the mean of population 2, then the difference between the two measures is mu1 minus mu2. It doesn't matter which one you put first, as long as you get the tails right. It doesn't matter which one you put first. So in order to estimate mu1 minus mu2, we will select a simple random sample of size n1 from population 1 and size n2 from population 2. I want you to notice right away that the samples don't have to be the same. Right? We can still do this test with two samples of different sizes. They do not have to be the same. We're still going to let x bar 1 equal the mean of sample 1 and x bar 2 equal the mean of sample 2. So our estimate is going to be the difference between those sample means. That, again, is not different from the previous chapter, right? We went ahead, we've calculated a sample mean, we differenced it from its mean. We're still going to have a lower tail test, an upper tail test, and a two-tail test. I don't like generally writing my test in this format. I like writing it this way, so it's clear to my eye which way I'm looking at the test. I like to see things relative to 0. 0 is pretty easy to know if you're on the left-hand side of it or the right-hand side of it. So I'd encourage you to write it this way, where 0 is going to be at the end. However, the top one is correct as well. Just as before, we have a problem of knowing our variance and not knowing our variance. We're going to just start right away with the hard one. We don't know what our population variances are. If you did, it'd be easy, and I can show you the formula for that. But let's do the hard one, because that one is a bit more complicated. All right. If we don't know what the variances are, and we think they're somewhat related, we can use what's called a pooled variance. So you're actually going to do a weighted averages between the two variances. And I'll show you the formula for that in a second. But you'd have to weight the average between the two variances and construct one. If we can assume that they are different from one another, the two variances, and they're still independent, it's actually really simple. All right, so we're going to talk about the pooled variance test. if the assumption is that we have different data sources, so they're unrelated and independent, the sample selected from one population has no effect on the sample from the other population, and the samples are randomly and independently drawn. So that becomes a problem for this Job Corps example. The reason it becomes a problem for the Job Corps example is that, let's say I was only grabbing it from one city. There are going to be some folks who just didn't get into Job Corps. Are they the same as the folks who got into Job Corps? That would be a bad grouping, those two there. A better grouping would be to grab one city that has Job Corps and another one that does not. So that way the ones that did not never had the opportunity to actually get into Job Corps. Then they'd be unrelated at that point. We still assume the populations are normally distributed. We still use this pedagogical rule that we want them to be greater than 30 for a Z and less than 30 we use a T. We're going to assume that the variances are equal to one another. If we do that, we have to make this weighted average of the variances. All right? Notice that the weighted average is really using the degrees of freedom for both of those variances. So here is the degrees of freedom for sample 1 and N1 minus 1. We multiply it times the variance for sample 1. Then we add that to the variance for sample 2. So this is N2 minus 1 times S2 squared. And then we divide through by the degrees of freedom from 1 plus the degrees of freedom from 2. Once we have that, then our formula looks kind of like this one again. Except that we're going to say that these two are the same. Now, one thing that's missing from here, or I shouldn't say missing, one thing that helps us here is that we said the two populations were independent. So if the two populations are independent, we can simply add their variances together. If the populations were not independent, we'd actually need a covariance term. That is the one type that we're not going to talk about at all. You're going to notice that in all of these examples, I'm going to assume that the two populations are independent from one another. And that is an assumption, a strong assumption. The other form you won't find in your book at all. So the form where the two populations are related, that one is not going to be in there. So once we have that, we're going to construct our T-stat. It's still going to be the difference between our sample statistics, so the difference between the two means, minus the difference in our nulls. So that part is the same as before. Right? Before we had just one X bar here, minus its null. Here our null happens to be 2 mu's instead of 1, so we're going to take the difference between those 2 mu's and compare it to X bar. We're still dividing through by a standard error. Just so happens that in this case the standard error has 2 samples in it. But still dividing by a standard error, and we get our T-stat from there. The degrees of freedom for the T-stat have to show that you do have 2 samples, which means it's going to be N1 plus N2 minus 2 degrees of freedom. But this is the same exact setup as we had in the previous chapter. Sorry. This is still the sample mean from the previous chapter. This is still the standard error from the previous chapter, and this is still the critical value from the previous chapter. Meaning its multiple is still the margin of error. Don't go back and relearn a concept you already know. Just apply to this new standard. Right? It's a concept you already know. This is X bar, this is the critical value, this is the standard error. So here's an example. You are a financial analyst for a brokerage firm. You are comparing the dividend yield between stocks listed on the New York Stock Exchange and NASDAQ. You collect the data below. Is there a difference in means between the NASDAQ and the New York Stock Exchange? So you go out and you find a sample of 21 stocks. You find the mean to be 3.27, and you find the sample standard deviation to be 1.30. You go out, you do the same thing for NASDAQ, only this time you grab 25 stocks. You find a sample mean of 2.53 and a standard deviation of 1.16. And now we're just asking whether or not the returns are about the same in the two markets. Right? Even though they have different variances, we can still answer that question. Are the returns about the same in the two markets? This is a simple two-tailed test. We didn't ask if one was bigger or one was smaller, right? We just said, are they equal to or not equal? So our null hypothesis is that they are equal to, that's the claim, that they have the same return. And our alternative will be that they are not equal to. So we're doing a two-tailed test here. We specify the level of significance with alpha. In this case, it was 0.05. and the sample size n. Well, we have two n's, so we also have 2 degrees of freedom we need to worry about. And then we have to do the weighted average between those two sample variances. So we're going to take 21 minus 1 times the standard deviation of the first sample, and we square that, plus the degrees of freedom of the second sample times its standard deviation, and we square that. Right, that gives us the weighted sample standard variance in the numerator, and then the denominator we're taking degrees of freedom from one and we're adding that to degrees of freedom of the other. So it's a weighted average. Whichever sample we have more of is going to tend to be more towards that sample variance than the other. In this case we get 1.502. Now this is still the sample variance between those two. It's not the standard error yet, right? In order to get the standard error we still need to do one more step. What's that? Well, that gives me a standard deviation. Still not a standard error yet.
It should be 1 over n.
Yeah. Now we got to go back over here and multiply times this 1 over n1 plus 1 over n2. And then take the square root. At that point, it's the standard error. At that point, it is the standard error. Because we still need to have it be true that as n gets really, really big, we approach the true population mean, all right? And as n gets really, really big, the standard error should get very, very small. Still wanted to hold that concept. So we do that, and we get a t-statistic of 2.040. So now we have to go out and we have to find what is the critical value for t. So how many degrees of freedom do I have then? 44. We go out and we get our critical value at 44. And we find that critical value is going to be 2.0154. Right? So this is the critical value. This is our observed value, 2.040. Do we reject or fail to reject?
Reject.
We reject, right? We're in the rejection region. That previous z is bigger than the critical value, so we have to be over in the tail. So we can say that the returns from these two stock exchanges are different. We didn't make the statement of which one's bigger than the other. We just said they are different. Step 5, determine whether to reject the null and state your conclusion. We found that the test statistic of 2.04 is greater than the critical value of 2.0154. So we have to reject the null hypothesis at the 5% level and conclude there is evidence of a difference in means. We can't say direction because that's not what the test was. We can say that there's a difference in means between those two. Confidence interval works the same way as the previous confidence interval worked, right? We take our sample mean, in this case the difference between the sample means. We do plus or minus the critical value, and we multiply it times the standard error. Same exact thing as we did before. In this case, our confidence interval is 0.9 to 1.471. Now I want you to see a little trick here for testing. Our test was that the two means were equal to one another. If you set it up as mu1 minus mu2 is equal to 0, then really what you're looking to see is whether or not your confidence interval contains 0. If your confidence interval contains 0, then you would fail to reject the null. If your confidence interval doesn't contain 0, then you reject the null. So here you can see that 0 is not inside of it. If anything, we can almost say that we know it's positive, right? If you set up the null hypothesis like I suggested, that second row, you would have had mu1 minus mu2 is equal to 0, right? Versus mu1 minus mu2 is different from 0. So what this tells you is that if you were to construct a confidence interval and the null was true, 0 should be inside of that confidence interval. Alright, so we did the left-hand side. Now we're going to do the right-hand side. Right? Mu1 and mu2 are unknown, and they're not assumed to be equal. We still use an S1 and an S2. Population variances are not or cannot be assumed to be equal, so solving calculations are much more complicated if we allow for correlation. If you don't allow for correlation, then it's just a simple standard error that I previously give you. But if they are correlated, then you get that nasty degrees of freedom formula. And you yourself can't calculate the standard error. You need a computer in order to do it. And the computer, you have to feed it the entire sample, because it has to calculate the covariance between the two populations. Now here's the easy one. easy in terms of logic to me. A paired sample is one where we have the same people before and the same people after, which means that instead of taking differences of the entire mean, we're actually taking differences per person. Right? So we're taking differences per observation. This one should reduce itself right back down to a one-sample test. That's the nice thing about these paired samples. So you want to test the hypothesis or form a confidence interval for differences between two related population means. A paired or matched sample is a repeated measure of a before and an after, and eliminates variation among sample items, thus reducing the sampling error. So what this means is that I can difference out individual effects and only look at the one effect. So one question that a lot of people want to know is, do teachers help? Right? Do they actually help students learn more? Or is it that, no, we all come in at 4 years old at some level of IQ, and we go on from there, and we're going to perform according to that. It's just a natural progression based off of our own learning. Or can a teacher actually move that needle? Right? In order to do that, there's something innate about you I have to get rid of. Right? There's something innate about your study habits, about the way you learn, that I have to get rid of. But it's unobserved to me. I don't know exactly what it is. I don't know exactly what your IQ is. But I want to evaluate this teacher. So one thing I could do is give you all a standardized test before you come into class, before you've had that teacher that first time. We'll use that as your baseline. And then we'll stick you in a class with that teacher, you'll learn something. And I'll give you the same standardized test afterwards. Then I get to take the difference for each one of you, because I'm not trying to compare whether or not the person who got 99 improves to 98 as being, oh, that person's now a 98 student. No, what I want to see is that difference, that they went up by 8 points. And that same improvement of 8 points down at the lower end would mean an improvement in the teacher. Assuming that, what you were being taught had nothing to do with the exam. It'd be something having to deal with the teacher that made that improvement occur. To give you an example of when this was actually done, let's use with regression analysis, but when this was actually done, the LA Times went out and they actually got data from the LA school system. Meaning they went out and they got the California Achievement Test. And they got to see the same student go from, essentially from 3rd grade straight on through high school. The same student, every time. And they knew what their California Achievement Test was at every level. So, they could then difference out the student effect. Meaning, they're going to be the rock star students who just always get A's even if I put a monkey in front of them. Right? They're just always going to do that. They're self-taught. And then there's going to be other folks that I could teach them everything underneath the sun and they could still barely write their name. And there's just nothing I can do about that. But if I have their achievement levels at every step along the way, I can take those differences. Now those differences are just individual differences, right? They don't tell me anything yet about that teacher. But if I have all those folks in the same class, well now I can take that first difference, which gets rid of the individual effect, right? The superstar or the dum-dum effect, right? And then I can take the mean across those folks over the entire class. That mean should give me the teacher effect, right? Because that would be the improvement or the dumbing down in the opposite direction of that teacher. And they did this. And they found, luckily on average, that most teachers do improve the performance of students. However, they did find a non-trivial number of teachers made students worse. Right? Roughly about 14 to 15% of teachers in the Los Angeles School District actually made their kids dumber after experiencing them. They went in the wrong direction. Now, to make things scarier, they gave this data to a bunch of economists. The economists went back and they didn't know who the teachers were. They didn't have them linked up. They just had teacher 1, teacher 2, teacher 3, and they went back. They calculated numbers. They gave it back to the LA Times, and the LA Times published the names of those teachers. And this was their fight against tenure in California, which they lost anyway. But that was a way of outing some of the problems that were occurring. And it was very hard for the school system really to say otherwise, because it's either they have to say that the California Achievement Test is a bad measure, which means that why are they handing it out then? Or they have bad teachers. So which one do you admit to? So they admitted to the bad teacher part, which doesn't help, because when you have tenure, all that means is they put you in a place you can't harm students. They still have to pay you. New York is infamous for this. They have what are called rubber rooms. Not really rubber rooms, but they are administrative offices where these folks walk in and do a crossword puzzle all day, and they have to get paid. Talk about waste. All right. So, how do we do it? Well, it literally is the difference by each individual. I get to see your before, I get to see your after, and I take that difference. So, a way to think about this is that each one of those X's is made up of a couple of parts. They're made up of before some error, because you can have a bad day or you can just get lucky, and your innate ability. And the after would still be an error. It'd still be an error, a different one, but still an error. It would still be your innate ability. But then there would also be a treatment effect. Okay? So then when you take the difference between each individual, what you're going to do is you're going to remove the innate ability part, assuming that that's constant over time. All right, if that's constant over time, you remove the innate ability part, and what you're left with is a difference in the errors, and then this treatment effect. Now, the difference in the errors is still noise, and that's why we need to still take a mean after all this. So after we take that difference, we still need to take a mean. All right? But these errors are individual errors now. And what we're trying to do is minimize those individual errors. And that gets us down to the old formula for standard deviation. Right? Before, instead of having b's, we had x's here. xi minus x bar. So now we can go ahead and we can test whether or not the treatment effect was 0, was positive, or was negative. And this is exactly what they do in clinical trials. What they'll do is a run-in period in lots of clinical trials. Well, they'll recruit a bunch of folks. They will put some in a placebo group and some in the treatment group. Initially, they'll give everyone a placebo, because there's something called the Hawthorne effect, right? Where because you know you're being watched, you behave differently. So they need to be able to capture that effect right away. So they're going to tell you that well, they're not going to tell you, but they're going to give everyone a placebo at first. So they can try to capture that Hawthorne effect and just take the difference between the two groups. Then they'll actually start giving, after some time period, the active drug to the treatment group. So they know when they give the active drug in, they know when they didn't have the active drug in, so they can get rid of the Hawthorne effect, and they can look at the treatment effect of looking at those two groups. Alright, so once you have that, this is the old t-stat we had before. Alright, here's x bar, here's our null, here's our standard error. Everything works exactly the same as it did in Chapter 9. So the match data set should look exactly as the Chapter 9 set, except that you have to construct it first. Alright? Everything else about it is the same. Any questions on this one before I go forward? So you can only use this when you have the same observations in the before and in the after group. They can't be different. So for example, they have to be the same sample size. If not, some new person popped up, or some person disappeared. Right? They have to be the same sample size. They have to be the same folks before and after. As long as that's true, then we can do this paired difference, and then we can treat it just like we did our one sample t-test. You'd even calculate your degrees of freedom the same way. You take the full number of people you have and subtract it from 1. So this is conceptually identical to the one sample. Alright, so here's our example. You send your salesperson to a customer service training workshop. You want to know if the training made a difference in the number of complaints. So you know what the complaint numbers were before, over a set period of time, to be fair, right? So we'll look at number of complaints you had over the past year. Then we send you to this training program, and we do it again, and we look at the number of complaints you have in the next year. And then what we're going to do is, for each individual, we're going to take their difference. So we're going to do 6 minus 4, 20 minus 6, 3 minus 2, all the way down. When we do that, that's going to construct our new data set, and we're going to ask whether or not the mean of the difference is equal to 0, meaning that the workshop had no effect, right? Or that the mean of the difference is different than 0. Here, since we only had 5 people, 1, 2, 3, 4, 5, our degrees of freedom are going to be equal to 4. So we do that. We go ahead and we take the difference. 4 minus 6 gives me negative 2. 6 minus 20, negative 14. 3 minus 2, negative 1. 0 and 0, and then negative 4. We sum them up, we get negative 21. We divide by the number of folks we have, which is 5. So it seems to reduce the number of complaints by 4.2 on average. I'll give you a real-world example after this. It'll be another story.
Why is it negative? Oh.
They're doing after minus before. So here's your mean, and then you can go back and you can calculate your standard deviation using the same rules we did before. So that means you take this negative 4.2, subtract it from negative 2, and square that. Subtract it from negative 14 and square that, and so on and so forth. So when we do that, we get a sum of 128.80. Again, we divide that whole number by 4, and we get 5.67. These are the same steps we did way back in week 1. We construct our standard deviation. It's still not a standard error yet, right? Just standard deviation. And then we take that standard deviation, we divide it through by the square root of n again to get our standard error, and we take that difference. And here we have a t-stat of negative 1.66. If we go to our table, the t would have to be 4.604. So do we reject the null hypothesis, or do we fail to reject the null? Here's your observed statistic, and here's your critical value. Fail to reject, yes. All right, we're still inside. We're not in the rejection region. We're still inside. So we fail to reject. Now I want you to know something. That 4.2 mean sounded big, right? You lowered the number of complaints by 4.2. But since the sample size was so small, it still wasn't enough to be able to say that there was a significant difference. And so since we're inside in the non-reject region, we fail to reject the null hypothesis. So we can't say that there has been a significant change in the number of complaints. Even though the point estimate is negative, we can't say that there's been a significant change. And in fact, if you look at the difference between each individual, everyone got at least not worse, right? There's one person who had none before and none after, and everyone else improved. Everyone else had a negative value. Even with that, it still wasn't enough because the sample size was so small. Alright, population proportions. They work, again, the same exact way. You still have the restriction of meeting this 5 requirement. So, pi times n1 has to be greater than 5. Pi 2 times n2 has to be greater than 5. And also, its opposite has to be greater than 5. Those are the same rules as we had before. The reason we need that rule is so that we can approximate the proportion using the central limit theorem, using that normal distribution. When it violates this, we can't say that it's normally distributed. Once we have that, it's as if we have these new means again, and everything works the same. We take the population proportion from the first sample minus the population proportion from the second sample, and that constructs our new point estimate. So how do we construct our weighted pi, right, or our observed statistic? Well, you take the total number of successes in one sample, add it to the total number of successes in the second sample, and divide through by all the observations. That gives you your pool proportion. Now, we're going to need that. We're going to need that thing.
And the x1 and x2 are number of successes?
Yeah. Okay. Now, here is where you need to be careful again. Notice what we're using in the denominator in order to do our testing. So like last time on Friday I said be careful, you have to use what's under the null. Well, here that doesn't work. So this is new. Or you want to write this down. This is different. Here we have to use that pooled P. Now this pooled P is different than this P up here. I'll go back to the previous slide so you can see what this pooled P is. This pooled P is different from the P that was up here. Alright? This is the sample proportion from sample 1. And this is the sample proportion from sample 2. But to get to this pooled P, we had to construct this weighted average. The other thing you want to know is that there's no pi's down here. When we did it with one sample, what did we use down here? Pi's, alright? No pi's down here. So be careful. Alright. Your tests are still the same. Again, I would prefer that you write it this way, relative to 0, but these are still correct. If you want to say pi 1 is greater than pi 2, then the alternative would be that pi 1 is less than pi 2. You can do the upper tail test, that pi 1 is less than pi 2, versus the alternative that pi 1 is greater than pi 2. And then the two-tailed test, the equal to and not equal to. So in these cases, you're looking at the lower tail, the upper tail, and the not equal tail. Notice that it's the alternative that gives you the tail that you have to look at. All right, again, this is exactly the same with the exception of the standard error. Exactly the same as what we saw in the previous chapter. Alright, so here's this one. Is there a significant difference between the proportion of men and the proportion of women who will vote yes on Proposition A? In a random sample of 36 of 72 men and 31 of 50 women indicated they would vote yes. Test at the alpha equal to 0.05 level. So let's try to do this one before we skip ahead to the slides. Alright, what is the proportion for men? What is the proportion for women? So what do we get here for men and for women?
5 for men.
How much?
2 for women. It should be 0.5 for men.
0.5 for men, and for women?
6.2.
6.2. Okay. Now I want you to construct the weighted average. So P bar.
Should be 0.5 for 0.9.
You're going to have 36, 31 over 122.
And it's 0.5 for 9.
0.549. Alright. And then we're going to use that to construct our standard error. So you use that to calculate the z. You get a z of negative 1.32. Since we are using a z statistic and we want to look at the 95% confidence interval, we're doing plus or minus 1.96. Since that is inside, so not in the rejection region, we fail to reject the null hypothesis that there is a difference in voting between the two genders. What's what?
Pi.
Pi here is the population proportion.
So we don't put that in there, the population proportion.
Well, that was from the null, right? So let's go back to the null. It says, is there a significant difference between the proportion of men and the proportion of women? So the null would be that there is no difference, right? So we're asking, is there a difference?
Okay.
So then pi 1 minus pi 2 would be 0. So then the confidence interval is formed the same way. You have pi 1 minus pi 2. The one difference here, again, is in the standard error. Here you got to treat them as being independent. And by treating them as independent, you're going to take the variance of one, add it to the variance of the other, and then take their square root. So there is no weighting here. Right. The reason we had to wait for the test was that we have to say under the null. Confidence interval is not under the null. Confidence interval is just saying what is the likelihood that the population difference is going to land in between those two. And that part is confusing. That's why I'm trying to repeat it over and over again. When you're doing a test, your standard deviation has to be calculated based off of what the null says. When you're just doing a confidence interval, that doesn't have to be true. And that's the difference between Chapter 8 and Chapter 9, when you go back to the one sample examples. So those were our two sample tests when we did population means. I'm going to hold off talking about variances until next class.